Great. First thing, fork it to my personal account. Random question. Is it easier to see my screen when I have dark mode on, or is it better if I flip it to light mode?
I prefer dark mode, but that's me.
Okay, I don't know if it's easier, read off screen, so just let me know.
It's easy on the eyes.
Okay, yeah, it's easy on my eyes, but again, I don't know if how the display or the optics are from Zoom. Okay, so I forked it over. I'm gonna quickly clone it. All right, let's get a VS Code open. I like moving around here. Okay, so binary search. Hopefully you guys had a chance to read the README, or at least took my description. All right, so they have a basic premise in the README, but I'm just going to dive into it. So let's take some of their test cases. So we have a super big array. In this case, we
also unsorted.
Pardon?
It is also unsorted, which could be a problem.
Yes, so that is a key element of binary search. It relies on the fact that your initial data has to be sorted. Otherwise, the binary search just won't work as you expect. So in this case, we have 8 items. So let's actually just code this up and kind of just talk about it. So we have this super big array. It's actually not that big. I'm going to add a couple items to it just for fun. They should be unique. Okay, so I have 10 items in here. Let's say we're trying to find something. Let's say we want to check if this list has number 9 in it. All right. So one way we could do it is linear search. This is something that we did in week 1, I believe. So if we want to do this quick linear search, we could do def linear search. And then we can basically, I'll pass in my array here. Pass, and then call linear search. And pass my super big array into that. All right, so we have super big array coming into here. Call that data. For x and data, if we need something to find, so let's say we're trying to find 9. That's our item to find. If x equals item to find, return. Return index. So yeah, usually when you're searching, you want to actually find the position, not just a true or false. So we're going to return I in this case. Okay, so basic premise here is looping over the index and the value. We're checking if the value equals item to find. If it does, we return index. Again, some criteria here. The initial list must have unique values, or I guess it can have duplicates, but in this case, it's easier to understand with unique values. For linear search, sorted data does not matter. When we talk about runtime complexity, again, we're going to go over this, I believe, on Thursday of this week. Linear search runs in O of n time. So I guess this is a sneak peek of complexity. When you see something like O of n, this means that as your input changes, your complexity scales on a factor of n. So this is called linear complexity. So for example, if my initial list were to grow to 1,000 items, my algorithm will scale linearly, meaning proportionally. So 1,000 items here means that this search can take up to 1,000 iterations. If it's 1,000,000 items in my list, then this could take up to 1,000,000 iterations. So again, it's proportional. As my data grows, my algorithm grows on par, basically. There are different types of complexities. There's O of n squared. Again, we're going to get into this. I'm not going to talk too much about it. This basically means as your input changes by a factor of n, your algorithm runtime complexity will be quadratic. So if your list goes from, let's say, 10 to 20, so basically doubles, your complexity, your runtime will be about 4 times as great. So it's going to keep scaling faster and faster as your data grows. Anyway, so that's linear search. Linear search, as I mentioned, is O of n. So it's not terrible. Linear complexity is considered mediocre, but we can do better. And that's where binary search is very important for our needs. Binary search, again, getting a little ahead of ourselves, is O of n log, it's log n. So log n is a lower complexity than n. And this basically means, again, the log comes from the fact that you're chopping it in half and half and half every time. So hypothetically, let's say we had 100 elements. We chop it into 250 bits, and then 25s, and then 13 or 12, and then 6, and then 3. So it's going to take, at most, I believe, like 8 searches, 8 iterations, effectively, rather than up to 100 if we had 100 items. So binary search, again, is just a faster algorithm. But it is more complex, so that's a trade-off, right? Linear search, pretty simple, for loop, find it. Binary search, way more complicated, but way faster. So there's kind of your trade-off of developer time versus execution time. So let's talk about binary search. But the most important thing must be sorted. And that is some trade-off that we're going to have initially, because to sort this item, this list, it's going to have some overhead, so that's going to reduce our overall effectiveness of this algorithm. But once we sort it, we can search it multiple times and find those items quicker. So let's sort it. Super big, say sorted. Data equals super big array. Is it just dot sort? All right, we'll check that out. So print sorted data. All right, now that it's been sorted, we should get something that looks like, actually, let's just run this and make sure my sorting is correct. We got some errors here. Got to pass that. Okay, so linear search is going to run. It's going to try to find this index, unsorted. So I guess there's some discrepancy there. We'll try to deal with that. All right, binary search. So it's through Python, binary search. Python. Okay, so we got none, meaning we didn't find it. That is not what I expect. Data. What did I do wrong here? All right, so that's our data called linear search, super big array.
You're not doing anything with the result. I think you have to print that.
Yeah, it should return. Gotcha. Okay, I see what you're saying. Thanks, guys. Yeah, need to print the results. In the case we don't find anything, we should return none. All right, there we go. So 7 is the index of the item we're looking for. So 0, 1, 2, 3, 4, 5, 6, 7. All right, that looks cool. But now we want to sort our data. So it's there. I'm not sorting this correctly. Is it sort? All right, can I look this up? So I forgot. Sort list in Python. I was doing it correctly. Does that actually sort the actual item? All right, so there's a sort method on list. It just exists. I'm not sure if that returns a new list or sorts in place. So I think it's in place based on my
That'll work.
All right, there we go. So it actually updates the existing array. It does not create a new array. So that's something to keep in mind. All right, so now once we have this sorted, we can take advantage of binary sort. Obviously, our index is going to be a little different than our original, but let's just go with our sorted array. So our goal here is to basically chop in half and try to divide and conquer, right? So we're going to check in the middle. And the whole reason we can do this is because now that we're sorted, if we grab a value, let's say we grab this 5, and we realize that 5 is in this position, and we're looking for a 9, then the 9 is greater, so we know we can just ignore all values beneath it. everything beneath this 5 is going to be lower than the value of 5. Let's actually change this up a bit so we get some non. Okay, let's run that. Okay, so change some values so the indices aren't straight mapped, but I guess they're still kind of in order. Regardless, our goal here is going to be chopping this and finding that 9 if it exists. So first step is we're going to take in our super big array and call binary search on it. So result equals binary search. And we take in super big array and item find. All right, so same general setup. Item find will be 9. Okay, so the question is, how do we implement this? All right, so conceptually, again, let's kind of pseudocode this and then try to create a general map of it. I'm not sure if I'm going to code it all. The first thing is obtain data, which is passed in. Second is find the midpoint, right? Because again, when we're trying to divide it, we want to divide it smartly, as in right in the middle, or as best we can. We don't want to like grab a random number and then try to check, because it's not going to be the optimal solution. So find the midpoint index. We need to find the midpoint index, and then we need to find the midpoint value. Find the midpoint value. All right, so we're just, again, trying to narrow down what's the middle item and check if that is, we have 3 cases. When we grab a middle item, it's either going to be the item we're looking for, which is great, we lucked out, and then we're done because we found the item. If the item we're looking for is greater than what we just found, then we got to search the upper half. If the item we're looking for is lower or lesser than the value we just found, we are going to search the lower half. So 3 cases. So that's what the midpoint value is important to us for. So obtain data, we have data. Find the midpoint. How do you find the midpoints? Let's query the audience. Sarah, how can I find the midpoints index for data? I'm not sure, you might be muted.
Still muted.
All right, I believe Sarah was getting at that we're going to first need the length of our data. So let's do len data, so we know how many elements there are. And then using length, we would want to divide by 2. So let's say mid index equals length divided by 2. So we're going to round down using integer division. Again, it doesn't really matter if we grab, slightly below midpoint or above, because when we have equal elements, it's not going to, there's not going to be no exact middle element. So middle index is where we're going to chop. In this case, we're going to round down. So if we have 10 items, our middle index technically would be like 4.5, right? But we want index 4 in that case. All right, so we get mid index. Next is find the value. So let's say mid value equals, who else do we have here? Thomas, how can I get the middle value here? You might be muted also. Hopefully I'm not muted here.
No, sorry, my mic was just physically muted.
Gotcha.
So we're not talking about like the index, but the actual middle value.
Yep. Yes, I got the middle index up here. How do I get like the middle the actual value that I'm trying to investigate?
Would you add the sum and get the I guess divide it all by the number of elements in the list?
So again, to clarify, so middle, I'm not trying to get the mean, no, I'm not trying to average anything. I just want like physically the middle value, one of these 2 values.
Oh, okay. It would not be similar to the way you obtained the index?
Correct. But now that I have the index, what is this index pointing to?
It should be, well, if there's an odd number of elements, it should just be the middle value. And if it's rounded, I guess whatever's close enough, right?
Right, but how do I obtain that value? So I have my index. I know that my middle index in this case is going to be 4 because I have 10 elements. So that middle index is going to be 4. How do I get the value from there?
Isn't the index pointing at the value?
Yeah. So again, yeah. So we want to just extract the value from our data. So we have data, which is our data set. So yep, middle index here, we computed that. So now we can grab the middle value. So in this case, it's going to be 7 because, again, integer division, this got rounded down to index 4 instead of, we don't want index 4.5 because that's not a real index. All right, so we get middle value here. And now, what do we want to do? So we kind of went over this, but let's go with Stephen. What was my pseudocode options here? I had 3 options. What were they? So I have my middle value. What do I want to do with that middle value? I'm not sure if you're muted also.
Hey, today been rough.
All right.
Wait, hold up.
What
was that?
You're good now. Yeah.
Okay. So what to do with the mid value? So when that mid value become the upper end of the like, I guess the bottom half, so to speak.
It will be, but what's the first thing we should do with middle value? So right now I'm sitting on this 7.
Mm-hmm.
I'm looking for something. How do I know where to look based on this 7? Like, again, we got the middle index, middle value. So right now we're on the 7. So middle value is equal to 7.
Mm-hmm.
So again, what's our ultimate goal here?
Trying to just subdivide it until we find our whatchamacallit, until we find our value.
Yep, item defined. But how do we know if we found it yet or not?
Oh, if mid value is the value item defined, that'll be
Exactly.
that'll be one of them.
Yep. So I think our first step here should be check if mid value is our item defined, right? Because again, we might have just gotten lucky and hypothetically our value we're trying to find was the middle item. That'd be like the dream scenario where we had to do one search. So we should definitely check. So if mid value equal item defined, return middle index. All right, because we always want to return index, not the value, because we already knew what the value was. All right, so yeah, we should always check first, because yes, we're gonna need to use upper bound or lower bound, but we don't want to ignore this number. Like we definitely need to check it. So now that we've checked it, we can kind of eliminate it from our, I guess, our space if this is not true. So basically, if we didn't find it with the middle value, then we need to do a couple other things. So Stephen, you're kind of getting to it. So let's assume this is false. Like our middle value is not what we're looking for. The middle value was 7, item defined was 9. What should we do next?
Let's see. I like to say we start from, how would we like use that as our upper limit and then kind of like go subdivided from like from the 0th index to the 4th index.
Gotcha. Yeah, so this is where the challenging part comes in. There's 2 general ways you could approach this. Basically, we're going to use recursion here. And recursion is basically going to search another area. Sorry, I made my code a little smaller just to fit everything. But so we hit the 7. The 7 was not our answer. Now we need to search this space up here. But effectively, it's the same algorithm, right? We just have a smaller search space to search. So imagine we just have a new list and we just want to search this space. We can just pass this data back to our binary search and say, hey, find it in this area instead of the entire list before, right? But there's a challenge of maintaining the actual index for your entire array. So let's pseudocode this. Determine where to check search next. So if mid value was less than item defined. So in the case where middle value is too small, we know that we need to search above it. So this is where we use the term lower bound and upper bound. So in this case, min value is going to be your new lower bound. What I mean by lower bound is that that's your starting point of your search. Upper bound is how far you're going to go. I guess that's not technically true. So lower bound, upper bound just means your range. So in this case, lower bound is going to be 7, upper bound is going to be 14. In the other case, let's say we're searching for a lower number. Well, then 7 would be your upper bound, and then 3 would be your lower bound, because that's the area you're searching there. So if mid value is less than item defined, then let's do something like return, sorry, if mid value is greater, sorry, less than item defined, we're going to call our function again. Again, we just talked about that. So data is just going to be a smaller subset. So we could do that. But the problem is we're going to lose track of our initial index. So this is where it gets a little tricky. One way to do it is you can pass in index values. So you could do lower index and upper index. And this is probably the preferred way to do it just because it's a little easier to mentally imagine. So lower index and upper index is basically going to be pointing at areas where we should start our search and end our search. So initially, lower index is going to be 0, which means we want to start at this point. Upper index is going to be the last index because we're searching all these items technically. But once we split, then our lower index becomes 8, and our upper, sorry, index would be of 8, and the upper index would be the index of the 14 here. Is that kind of making sense? I want to pause here because I feel like I haven't paused for questions. Okay, so we need to figure out upper index and lower index, but initially lower index should be 0, upper index should be length of data. So let's make this none and none. Initially, when we call binary search, we're not going to specify lower index, upper index. We'll just kind of default them none. And then if we have none, we can say if lower index equals none, then lower index equals 0. This is our initial case. If upper index equals none, upper index equals length of data minus 1. That's the last index. All right, so this is initializing lower index and upper index for the very first time we come into this function. Every other time we're calling this function, we're going to pass it specific lower index and upper index values. So what I'm going to do here is, if this is the case, again, middle value is less than what the item we're trying to find, we want to search everything above it. So this is where we would call return binary search, but now we have a smaller list effectively. All right, so we're still going to pass it data. We're not going to modify data. And the reason being is because our indices are going to tell us where to search, not data itself. So if I pass data, we're still looking for item to find. The lower bound is now going to be middle index, because that's where the middle value was, plus 1, because we don't need to search this value again, right? We just checked it right here. So I do something like middle index plus 1. This is going to start at this 8, right? Because the index, middle index was for the 7. So middle index plus 1 will be pointing at this 8 now, because we already investigated this 7. And then we still, our upper bound is untouched, so we'll do upper index. We'll just pass that back to our function. If it were the other case, which I guess we should code up, and I know we're running short on time, so hopefully this will get you a good starting point. Elif and elif. We probably don't need this actual if condition because that's the only remaining condition, but always doesn't hurt to be more explicit. So in this case, if the middle value were greater than the item we're looking for, so again, hypothetically, so we're searching for this 4 and we hit this 7 in the middle, then we'd want to basically pass it the lower index. So lower index not going to change. We're still going to start our search from the bottom, but upper index is actually going to change to middle index minus 1. Okay, does that kind of make sense? That's how we're slicing it. We're not touching data. We're just changing our search space depending on what we found in the middle. Okay, so now that we have lower index, upper index, we should change our math a little bit. So instead of calculating length this way, we should do length of upper index minus lower index divided by 2. I guess that should be not divided. So the length of our space is now the difference in the index, right? So we start at index 0 and then go to index 9. The length of our array is 9. Did I lose a number there? So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10 items in here, so we should probably do a +1. All right, just to be clear, so we're taking the difference, adding 1, and that's how many items we're going to search through. All right, so now length is not dependent on data because we're not modifying data, we're tracking it by index. The other way to do this would be to chop your data each time, but then you got to keep track of your starting index. Again, there's 2 different solutions. I don't want to confuse you guys, so I'd say this one, again, is a little easier to implement in my opinion. All right, so now we have upper index and lower index. These values are being changed right here. So every time you call binary search again, it's going to be a smaller slice. So depending on where you're trying to search, either the lower index will change and be referencing the current middle index, or your upper index will change and be your new middle index. Again, the +1 and -1 is just ignoring middle index itself because we already checked it here. All right, so it's going to keep making your search space smaller and smaller until you either find what you're looking for or you don't find it if you have one element to search. There's going to be some additional logic that you need to check here. Basically, you want to make sure lower index is always less than or equal to upper index. It can be off, especially when you're doing this +1 and -1. So make sure you have your proper checks there. Did that kind of make sense? I want to make sure everyone's on a good footing before we break apart. Does the general idea make sense? So again, you're just trying to slice your search space each time. And by passing in indices here, you're going to get the correct result because you don't have to worry about having the correct index when you find it. Questions, comments? You guys just want to end Monday?
No, actually, you explained a few things. And when me and Don was doing it, there was a few issues that we had, but you cleared it up.
Gotcha. Again, definitely a challenging algorithm to implement. So don't feel bad if you're like, well, binary search seems simple conceptually. Why am I not getting this? It's, again, comparing to linear search, right? 4 lines of code versus up to maybe 20 lines of code here. There's a point for this. Again, I think we'll have a face-off, or I'll definitely try to make time for a face-off between linear search and binary search, and you'll see how much of a difference it actually makes with large data sets. So that's to come later in this week. Other than that, hopefully you guys give this a try and kind of can conceptually do it. Again, everything I coded here is not fully 100% correct, as in you're gonna need to make sure your indices are correct, as in you don't want them to get swapped, or this might run forever then. But yeah, that's binary search for you guys.
Appreciate it.
What else?